yes, test on Monday. You certainly don't want to be late. You want to get a good start, be here. Okay? So you can get comfortable, etc. Really can't have students coming in at 8 o'clock, 8:05, etc. You'll be disturbing everybody else, okay? So don't make that happen. Don't let that happen. You're doing a disservice to yourself if you're rushing in and trying to think you're going to do well on a test. Okay, guys. Aromatics, benzene, and lots of other different aromatic compounds. We were doing MO diagram of butadiene. And next week we start the 8-week lab, yeah?
Yeah.
The sulfanilamide report, due when you come to lab next week. And I sent out an email a couple of days ago including the NMR stuff related to the sulfanilamide report. Any questions about any of that? Okay, quick review. I don't want to spend much time. Let's move ahead to benzene. But MO of butadiene, importantly, it's got 4 p orbitals, right? And 4 pi electrons. All right, and this is what we used when we were doing our MO diagram. Molecular orbitals, sort of akin to hybridization. In hybridization, we took atomic orbitals and we mixed them and made new atomic orbitals. We call them hybrids. And then sp3 is a hybrid. But it's still an atomic orbital. With molecular orbitals, you take the atomic orbitals that are more than just on one atom, but over the entire molecule, and you're combining them. And when you combine them all, you create one orbital. But it's spread over the entire molecule. Now this is a little bit more advanced. It's a lot based on math. It's harder to draw these. But that's sort of the general idea. And so one orbital spread over the entire molecule is called a molecular orbital. And each orbital will hold how many electrons? Same as always. But the energy for the orbitals we drew, energy 4, right? Energy. There's going to be a midline that cuts through these always. The bottom 2 were bonding MOs. The top 2 were anti-bonding MOs. Okay? This came from looking at the interactions that we had. All right? For example, this third one here, by the way, number of nodes. 0 node, 1, 2 node, 3 node, 2 nodes. Here, I don't know what it was. If this was plus, this is minus, that's plus. This is this MO here. These orbitals are interacting this way to give one orbital now. This here is what type of interaction? We call that an anti-bonding interaction. Because the orbitals can come together in 2 different ways. They can come together constructively and reinforce each other and build, or they can come together destructively and cancel each other out. And this is like waves in a lake or something. Waves come together and make a bigger wave. But you can actually have waves come together and go silent. Same thing with sound. You can have pockets where there's no sound because the waves cancel. Destructive. That's what's going on. Destructive is an anti-bonding effect. This here is a what?
Bonding?
This implies same phase. Same phase is constructive, good overlap, and we call that bonding. But then what do we have here?
Anti-bonding?
Anti-bonding. What's the net here? 2 anti-bonding, and then a bonding, which sort of, this cancels each other out, and you're left with what net?
One
Anti-bonding net. That's why we call this an anti-bonding molecular orbital. We'll do more of this when we move to benzene. I'm not going to go exactly all through here. Once you set up your energy diagram of these are my 4 MOs, I have an idea what they look like. Then you put your electrons in, just like always, off-call principle, Pauli exclusion principle. How many electrons we have to put in here?
4.
4. 1, 2, 3, 4. And in this molecule, if you do an MO description of it, we say that the 2 bonding molecular orbitals hold the electrons, and the 2 antibonding molecular orbitals sit empty at ground state. But what this does give you is, whenever we do UV vis and we say we excite an electron, I mean, to what? If you consider all these just bonding pairs, I mean, what do you mean excite an electron? Well, here you can see what we mean. We can take one of these electrons and excite it to an antibonding orbital through absorption of energy, and now we have a better explanation of that. Lots of theory here, lots of math involved here. We're going to do enough just to do enough. Why are we doing it? Because this is what we have to do to explain why this guy is so unstable compared to benzene, which is quite stable. The regular valence bonding that we've always done doesn't give you the answer. It doesn't tell you why the 4-member ring is so unstable. We need to do this. Again, you can take advanced classes where you do half the class about this stuff. Okay? We're just going to do enough. Let's do this with benzene. And we'll do some of the same exact ideas. Like I mentioned in the other handout, I give you key to drawing MO diagrams for cycloconjugated systems. I recommend reading this. Everybody with me? Free information, no charge. Okay? That's what we're doing. Everything we're going to do here is outlined there as your steps. Okay. How many p orbitals we got here? 6 p orbitals. How many pi electrons in the system?
6.
Yes, 6 pi electrons. We can say this. How many p orbitals did we have in the previous example? 4. 4 p orbitals gives you 4 MOs. 6 p orbitals gives you 6 MOs. Yes, that's always like that. Okay. Okay. I'll try to draw the actual MOs here. I'm going to draw just the framework here. I'm going to hopefully do like this. I'll start kind of low. I could draw all these orbitals here again and put a sign in each. Instead, I'm just going to put a sign. Okay, p orbital. What's the best that all these 6 can overlap? And then we have the best over there. Here's the bottom. What's the best way these can overlap? The best way is where they're all in phase. All 6 are interacting constructively. That's the best. Best meaning the lowest in energy. How many nodes here?
0.
0. A node would be something like this. That means there's no electron density between here and here. That would come from no overlap, antibonding interaction. But we have interaction all the way around. 0 nodes. Your first one has 0 nodes. 0 nodes. 1, 2 nodes. 2 nodes I drew. 0 nodes. Okay? There's your best MO. It's a orbital where the original 6 atomic orbitals are interacting nicely all the way around. And that generates 1 MO. This is how we're going to show it. Okay, next. Importantly, once it's cyclic, we have symmetry. And because of symmetry, the next level is going to have 2. All right? How many nodes at this level?
One.
1. 0, then 1. We can use the node to help us, okay? And the nodes are symmetrical. I draw one right there. If this is plus, what is this?
Minus. Or
No. There's no line between them. There's overlap there.
all of them are plus and all.
Yeah. But here we have a line between the two. That means there's no electron density, there's no constructive overlap. That means this has to be
Negative.
different phase. So there's minus. What about here to here? Is there overlap here?
No.
No. Yes.
Yes, there's no node going between them. Node went between here, minus, minus. These 3 are interacting, those 3 are interacting, but this one and this one are not, leading to no electron density between here or here, and we end up with a slice through there where there's no electron density. We call that slice a node. Because of symmetry, there's another way to get just one node. And it actually runs right through 2 atoms. And if this is plus or minus, it doesn't matter. It just, starting point, what would this be?
Plus.
Plus. Now, there's actually no electron density on this carbon. If you can imagine that. Over here.
Minus.
Well, these 2 are not even next to each other. So you could say plus here, and there's still no interaction. But things are symmetrical. This phase and these phases are opposite. But there we go. What about energy and net here? What's a net here? This is a bonding interaction. Bonding, 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 bonding. 6 bonding net. What's the net here?
Bonding.
This is a bonding interaction. This is a bonding interaction.
Bonding.
This is a bonding interaction, and that's a bonding interaction.
That's 4.
What is this?
Anti-bonding.
Bonding.
Antibonding. And what is this?
Anti-bonding.
Antibonding. What's the net here?
2 bonding.
To what?
Bonding net.
2 bonding net. 2 bonding net. It's still a bonding molecular orbital. But it's not as good as the 6 bonding net. So it's higher in energy. What's the net over here?
2 bonding net.
Series.
2 bonding net. The rest is nothing. They're not adjacent. They're not doing anything. They're not constructively or destructively. That's it. Both of these have the same energy, 2 bonding net.
But are they both equally stable?
Yes, they have the same energy. That's what I mean by the same energy. They're degenerate. You should have heard degenerate in Gen Chem.
But
Orbitals have the same energy.
when you move the electron density out of the atom as instead of between the bonds, wouldn't that like have a different effect between the two?
There's lots of peculiar things here.
Okay.
There's lots of questions you could ask. Again, that course, chemistry 4850, quantum, that's where you. All right, we're going to do enough. Good question. My answer is they're degenerate. They have the same energy. Yes. Okay. There's 3. How many MOs are we drawing here?
We have draw 6 total.
6. 6 p orbitals give 6 MOs. Because 6 p orbitals can interact in 6 different ways. Okay. Let's try the next one here. How many nodes here?
2.
Uh, 2.
Yeah, each level you go up, you have one more node. That's supposed to be a 6-membered ring. The nodes are here. My ring is not exactly perfect. Boom. Boom. 2 nodes. If this is plus, what is this? On the other side of the node, it means there's no overlap, so that must be opposite phases, right? What is this?
Same, minus,
There's overlap here, because we don't have a node here. Here.
plus, minus.
How about that? Those 6 are interacting that way. Did I get it right? Right through here, there's no density, because there's no overlap here, and there's no overlap here. It's destructive. But we do have overlap here and here. What's the net here? This is a what?
Anti-bonding.
Anti-bonding. What is this?
Anti-bonding. Bonding.
Bonding.
Anti-bonding.
Anti-bonding.
Anti-bonding. Bonding.
What's the net here?
2 anti-bonding.
2 anti-bonding net. This is an anti-bonding molecular orbital. There's another way to get one like this. Boom and boom. If that's plus, that's minus. I'm not entirely sure what we want to do here. If this is, if that's plus, that's minus. These are too far apart to have any overlap. You have nodes right through 2 atoms and through here. What is this?
Anti-bonding.
Anti-bonding and this.
Anti-bonding.
Also 2 anti-bonding net. Degenerate. Same energy. The last one is going to sit up here. And it has 3 nodes. How do we draw the 3 here? I think it's like this with another one. I think it's cross and one like here. And if this is plus, what is this?
Minus.
And what's the net here?
6 anti-bonding.
This is the worst way you could, it all 6, none of them were constructively overlapping. 6 anti-bonding net. That's the worst. Highest in energy. If we clean this up and just show the energy levels, we have 1 down low, then we have 2, then we have 2, and then we have 1 here, yeah? Energy, this is just the energy level diagram. There's an energy midline that runs right through here. And orbitals, MOs below the energy midline are
Bonding.
bonding molecular orbitals, bonding net. Those above are,
Anti-bonding.
yes. Here we go. Put your 6 electrons in. Where does the first one go?
The bottom.
Here. Where's the second one?
The,
Next to it.
There. Third. Where's the fourth go?
And the one next to it.
What is that called? Hund's rule?
yes.
Something like that.
You fill degenerate orbitals singularly first before you start pairing up in that Hund's rule.
The one.
Then we come back 5, 6. There's benzene. What do you see?
All good bonding.
Oh, the bonding molecular orbitals each hold 2 electrons. All electrons in bonding MOs. That's a good thing. Another good thing, though, all electrons paired. That's another good thing about benzene. And this in particular is the most important. And this is going to be aromatic. Okay, there's actually a picture of these MOs in the handout. There they are. This is looking down from kind of the top. Okay? This one here, bonding all the way around, the best. The dark is electron density. You got electron density all the way around. And 2 electrons sit in this orbital. Again, it's like fascinating and peculiar. What do you mean an orbital? Yes, it's one orbital spread over 6 atoms. It's called a molecular orbital, and 2 electrons sit there. But then you have 2 electrons sitting in here and here. And you see the node? The node is a plane where there's no electron density, cutting right through the molecule. We have a node here. That's actually, yeah, same thing. See, I cut the node through. See, I'll color on it, don't do that. We've got electron overlap there and electron overlap here, but none right between. You see, that's like this. And that is an orbital. And 2 electrons sit there. And the electron density is both up here and down here. Somewhat akin to like a p orbital. When we say the electron density is both above and below in this dumbbell shape. And there's actually in a p orbital, I don't know if you called it in Gen Chem, but that's a node in a p orbital. Probably didn't use that term. But the electron density is not there at the nucleus. But that's still an atomic orbital, an atomic p orbital. This is a molecular orbital because this is just one atom, like a carbon. This orbital is spread over 6. All right? And then you see the nodes? Look at the top one, how that's one orbital. Okay, you gotta kind of just, you can't think too hard on that. It's a lot of theoretical, a lot of math. Okay. What's up?
So many questions, but I'll start off.
That's good.
Do we know why the molecules behave like this? Like, why does this happen?
Why does what?
Why are these nodes created? Why is the electron density shifting? Why?
It's a lot of math and physics of electrons. And actually, there's a term called mathematical combination of atomic orbitals, MCOA. A lot of math built into this, leading to this. How do particles interact? Okay. All right, but you see how the picture of those nodes sort of is. That's what I tried to put over there with my plus minus. Okay. Okay, let's do this for cyclobutadiene. This guy. How many p orbitals in this cyclic conjugated system?
4.
How many pi electrons?
4.
There we go. That's a starting point, right? Okay, I'm going to do this sort of backwards. I'm going to start with this and sort of show you that, how you can start with that. Because anytime you do these, there's always going to be one at the bottom. Because there's only one way for it to overlap best. What is that? That's where all four are constructively overlapping. That's where I'll draw it over here, I reckon. And for some reason, I like to draw it. I haven't drawn this in a while. Let's see if we can make it still skewed. Let's see if we can get these drawn right. Okay, here we go. Four-membered ring. I just turned it a little bit. What's the best way for these four to overlap? These are p orbitals. They're going to overlap. There's only one way to do that. You're always going to have one at the bottom. Okay? Then for a cyclic system like these, you then go 2, 2, 2, 2 until you run out. Now you may run out with one at the top, or you may run out with just two at the top, depending on the number. I reckon if it's an even number, we're going to have one at the top. But if it's an odd number, we're going to have two at the top. 1. How many do we got? How many MOs are we drawing in our? 4, because we got 4 p orbitals. 1, then 2, then the fourth one is just 1 at the top. And that's always going to be the case. Again, could be 2 at the top. Because if we were doing 5, it would be 1, 2, 2, for a total of 5. What is this? 4 bonding net. Everybody agree? How many nodes is this one going to have? 1. Sometimes I'm not quite sure of the nodes. We'd have to look. If I do this here, if that's plus, this be minus. What's the net here?
0. Or 1 amp.
What's the net here? Louder? 0. Why?
There's nothing bonding, there's nothing anti-bonding.
Right, there's nothing bonding, there's nothing anti-bonding. Because I'm showing no electron density here. This is just too far apart to be doing anything. 0, it's neither. This is what you call this. It's not bonding or anti-bonding, we call it non-bonding. I'm going to say 0 net equals non-bonding MO. By the way, I didn't point out over here. Where's the midline here? The midline actually cuts right through these 2 MOs, symmetrically through. 2 MOs sit on the midline. Molecular orbitals that sit on the midline are non-bonding molecular orbitals. They're neither bonding nor anti-bonding. It's non-bonding. It's going to sit on the midline. But the midline is always symmetrically through in terms of energy. I don't know why I can't draw this like this anymore. Maybe I never did. Getting sort of skewed. Maybe I do it like that. There we go. I need to draw my lines that way. Now it looks like a nice square. The other, I don't know if we need to run through the carbon. It doesn't matter for us. If we do it like this, if that's plus, that would be what? Plus. Minus. What's the net here?
0.
Bonding. But what's this? Anti-bonding and that. And what's the net?
0.
0. Both of those are non-bonding net. They're going to fall on the midline, and indeed they do, based on symmetry. Okay, what's the... how many nodes for this guy?
2.
I reckon we can do nodes like this. If that's plus, what's this? This is the worst. It's where none of them are interacting, and what's the net here? 4 anti-bonding net. High energy, anti-bonding, above the midline. There you go. There's your energy diagram for your 4 MOs for cyclobutadiene. How many pi electrons?
4.
4. Let's put them in. 1, 2, 3. Where's the next one go?
The other one.
4. There you go. What do you see?
It's unpaired electrons.
2 unpaired electrons. The unpaired electron is called a radical. It's a diradical. Not only that, the 2 unpaired electrons are sitting in what type of MO?
Neutral.
Neither.
At 0.
A non-bonding molecule. That's also bad. Now this is the main thing here, because we will see some aromatic compounds with electrons in non-bonding orbitals. That's not, the main thing here is paired or unpaired. The fact that these are in non-bonding MOs is even worse than if they were in 2 electrons in bonding MOs. Yes?
Will we be able to analyze those compounds and see if those unpaired electrons will be reactive with other?
Well, you might just kind of predict they may be reactive. I don't know how much analyzing we can do at this level and for what I know. Okay. How stable do you think a diradical is?
Not very stable.
It's not very stable. And remember, what do we say about this compound? Very unstable. It can only be observed at like super cold temperature. To let it warm up, it's going to self-react. It doesn't want to exist like this. But again, we can only see that by doing MO. If we just say, hey, they're both resonance stabilized, they're both conjugated systems, why the peculiar difference in the reactivity? The huge difference. You have to do an MO diagram to see. It's a diradical. Very elementary look at MOs, but is everybody convinced now that the difference in the two? Question.
What does it self-react to?
I think it makes an 8-member, an 8-carbon product. 4 plus 4. Good question. It kind of does sort of Diels-Alder type chemistry, because it is a diene and the other single bond. And okay. All right, there we go. Let's move ahead here. Not a happy camper. Diradicals, not a happy camper. Question.
Yeah, for the second energy level there, did you not make a vertical node because it would have been the same as the horizontal? So we could have done a vertical node instead of that horizontal?
I'm not sure. I'm kind of thinking that in my head. It might be the same. I don't know the fine details there. Maybe I should, but I've never thought it was important enough to.
So when we draw our nodes, just draw nodes that'll give us 2 different nets? Is that what we should do?
Yeah, that's kind of what I'm doing.
Okay.
I know they're going to be degenerate, so I show my net should end up being the same. I know there's 2 because I just tell you that when it's cyclic, because of symmetry, after the first level it's going to be 2. Okay. Roman numeral 5 down here. What is this? Oh, Huckel's rule. Now we're going to be doing 8-member, 10-membered rings, all these. Okay? Do you have to always do this whenever you look at any new compound? Well, you can, but there's actually little rules. It's like in NMR, we have the N+1 rule. I mean, you don't have to sit down and look at all the perturbations for neighbors, you know, like I did. You can just say N+1. So it's a helpful little rule to get us the answer quicker. Well, Huckel's rule sort of gets us the answer quicker here. And Huckel, after doing lots of these, he said, I see something consistent here. A cyclic conjugated pi system with 4n plus 2 electrons will be aromatic. All electrons paired in the MO. Now what is 4n plus 2? What is n? N is just some integer. It can even be 0. If n is 0, what is 4n plus 2?
2.
2. What if n is 1? 6. And 6 is called a Huckel aromatic number. 4. 4 electrons. Can you ever get 4 out of this by putting in n as an integer?
No.
A whole number integer?
No.
No, you can't. 4 is not a Huckel aromatic number. You would never expect 4 to be aromatic. Basically, it has to do with the way you do this. And the more we do, we'll see. Whenever it's 4, or whenever it's a 4n number, that is anti-aromatic. And just that's the way it turns out. Because if this happened to be 4 MOs but 6 electrons, don't put this in your notes, we would come back and we'd do, now we have 6. 6 is a 4n plus 2 number. And if you have that type of number, you plus the octants paired. So 4n, we're in, well, n can't be 0 here because then 4n would be 0. But it can be 0 here, and this would equal 2. But basically 4n numbers. If n is 1, that's 4. If n is 2, that's 8. If n is 3, that's 12. 4, 8, 12. What's next?
16.
16. All those numbers are going to be what? Anti-aromatic. And any 4n plus 2 number, that would be, if n is 0, that's 2, 6, 10, 14. Those are always going to be aromatic or paired. All right? Let's do some more, though. How about this guy? First question. Is that a cyclic conjugated system?
Yes.
Fully cyclic conjugated system?
Yes.
Yes. Did you say yes? Who else says yes? I just wanted for the record. Who says yes? Fully cyclic conjugated? Okay, we'll have to come back and ask that again. Since it is, we can do what we're doing. Okay? Do you expect this compound to be aromatic or anti-aromatic?
Anti-anti.
Why so quick? 8 pi electrons, and 8 is a 4n number,
Yes.
where n is 2. Huckel's rule tells us it should be anti-aromatic. So what type of behavior would you expect this compound to exhibit? Happy camper?
No.
No.
Probably stabilized.
Could I have this compound at room temperature and work with it and do reactions with it?
No. Probably not.
Well, you certainly can't with that compound.
It's a little high.
Well, let me tell you something. This compound is a happy camper. It's very stable. You can distill this compound. It's fine. Very stable. Does that sound like an anti-aromatic compound?
No.
No, it doesn't. So what's going on here? First off, let's do an MO real quick. I'm not going to go through all the details. I'm just going to do the quick version so you can see. Let's see. 8 is going to be in terms, I'm not going to do the MOs, just the 8. We're going to have 1,
I think it's all here.
2, 2.
No.
How many is that? 7, 8. There you go. Where's the midline? It actually is going to run right through here. Do I have 8 up here? Okay. How many pi electrons?
8.
8.
But they're unpaired.
Okay, I'm not going to label this. We know these are bonding. What do we see here?
Unpaired neutral electrons.
A diradical. But Huckel told us it was going to be a diradical. He noticed this, and that's why he made this simple rule. That's what Huckel rules tells us. We knew we were going to get a diradical when we did this. But what's the problem? Here's the problem. It's not a cyclic conjugated system. But for the record, everybody raised their hand and said it was. It's not. Why is it not? What?
I'm guessing it's not planar.
It's not planar. Not planar. Here it is. If it was planar, it would be a cyclic conjugated system. Because every carbon has a p orbital. If I had 8 hands here, I could hold a p orbital up on each atom. There's 2. Imagine 6 more. They're all straight up interacting. Looks like a cyclic conjugated system. Let me ask you a question. Does this molecule want to be a cyclic conjugated system? Does it want to exist like this?
Yeah.
Yes.
No.
Why would it want to be a diradical?
Oh, okay.
No. Do I want to walk around all day like this? I have a choice. I'd rather walk around all day like this. Molecules have choices. They have energy wells that they seek out. This guy can avoid being a diradical by just doing that. It exists as a tub-shaped molecule. Now, it's nothing but 4 alkenes. Because now, there's 1 alkene, and I'll see if I can hold this right here. Can you hold? Stand up. Hold that right there. There's 1 pi bond. And the next door p orbital, turn it. The next door p orbital, or pi bond, is like this. I mean, this is still 90 degrees to the sigma framework that hybridized. Next door is like that. And this is not interacting with that. They're turning. Because for p orbitals to interact, they have to be side to side. If they exist like this, they're not interacting. What you have here is, this is just 4 isolated alkenes because it exists as a tub shape. It's not a cyclic conjugated system. And since it's not a cyclic conjugated system, everything we've done doesn't work. The MO only works for cyclic conjugated systems, what we're doing. Here's the problem. How can you tell by looking at it on the board? It's hard to tell.
That's some name though.
Well, yeah, but we also call that cyclobutadiene. It's the same type of nomenclature. Why is that anti-aromatic? The 4-membered ring doesn't have enough flexibility to become non-planar. But this one does. All it has to do, by the way, when it's like this, if this is sp2, that's supposed to be 120 bond angle. Actually, it's a little stretch there. And actually, if you can hold it in your hand, whenever I do this, you're going to feel the bonds going. Right now they're stretched, but now that also gives you a better bond angle. All right? And we call this molecule, is it aromatic? Certainly not. It has to be a 4N plus 2 to be aromatic. Is it anti-aromatic? No. What do we call it?
Non-aromatic?
It's just called non-aromatic. The same classification we would give to water. Water is non-aromatic. Or butane. Butane is non-aromatic. Non-aromatic, it's not cyclically conjugated. Okay? So, you have theory, but sometimes the molecule doesn't want to behave according to the theory. There's actually relatively few anti-aromatic compounds because many of them avoid it somehow. Okay? All right, let's look at some other ones here. How about this guy on the left here? Aromatic, anti-aromatic, or non-aromatic? What would you predict here?
Aromatic or non-aromatic?
Does it look like a cyclically conjugated system? Does every atom in the ring have a p orbital? Yes. How many pi electrons in this system?
10.
Okay.
10. Is that a 4n number or a 4n plus 2?
4n.
4N plus 2.
4n plus 2. And Huckel says that should be aromatic.
Now, is it planar?
Very good. The question is it planar? Now, it certainly would want to be. But maybe there's something that keeps it from not being able to be. Well, let's go back to data. And certainly the answer is not anti-aromatic. Certainly that's not the answer, because it's not a 4n number. It's either aromatic or non-aromatic. If it's planar, it's aromatic. If it's not planar for some reason, and the conjugation is broken, then it... How would you determine it? I've got that compound right here. How would you determine the answer? We can do all the theory we want, but we got to determine the answer right here. Tell me what you would do.
Graph the MOs.
Do it.
Did you graph the MOs?
That's just theory.
Would it be like,
This is just theory. We could do an MO and it looks like it's aromatic. Just like for the just like you can do an MO here and it looks like it's anti-aromatic.
Would you have to run like an addition reaction and see?
Tell me more.
Because before you wrote the one that's not in the plane, the last example we did, if you can run like a simple addition product with, or reaction with PR2.
Okay, you're getting, if it's aromatic, how do aromatics react with, like, for example, bromine?
It's very specific.
Don't.
Well, they do. You have to use like an iron catalyst, but okay, we went through this. They were labeled 1 through 4. They were experimental evidence for aromaticity. That's what we're trying to get. Do we have any experimental evidence we can collect on this compound to determine if it's aromatic? One of them was reactivity. Aromatic compounds react with electrophiles to give what type of product? Substitution. Where simple alkenes react to give
Addition.
addition. So, for example, we could react it with bromine and see if we get a substitution product or an addition product. Is it just 5 alkenes? Or is it a special aromatic system? What else could we do? NMR. What would you expect? What would you expect if it was aromatic? Signals in the 7 to 8 ppm range. What if you ran the NMR and the signals, by the way, it would just be one signal. What if the signal was at 5.2?
That's just,
The
That sounds more like just plain alkene.
yes.
Yeah, NMR. Anything else? Heats of hydrogenation. Because if it's aromatic, that implies a unique stability. It would be much more stable than if it was non-aromatic. If it was non-aromatic, it's just 5 alkenes. It's aromatic, it leads to this unique stability, and we would expect a lower H of H. We went through all this. We're back to that. This is the question we were looking at how to answer here, because the theory can tell us it's aromatic. Maybe it's not for some reason. Well, I know the answer. The answer is that is an aromatic compound. It exhibits aromatic properties. All right, I know that. Let's look at the next one. What's the difference in these two? They're both 10 pi electrons. The difference is this is all cis. All those alkenes are cis if you look at them. But the one in the next one, 2 of the alkenes are trans, and so it makes the ring look like that. What's the answer here? Aromatic? Anti-aromatic? Non?
Either aromatic or non-aromatic.
Yes, it's certainly not anti, because 10 is not an anti-number. If you did an MO, it would look aromatic. But again, that's just theory. How could we prove it? NMR. Well, I know the answer here. The answer here is this is non-aromatic. What?
I don't understand like how we can come up with a definitive answer if we're not given any other pieces of that.
You wouldn't be.
Okay.
You wouldn't be.
Because I'm already just looking at these like, think about these next ones
No,
down
you'd
below.
you'd have to have more information.
Okay.
I'm just sort of giving you the answer, and I'm just going to tell you the why part.
Okay.
Because we do have a time limitation, but you're exactly right.
Okay.
But what I'm getting at is, hopefully you understand what data you might ask for.
Okay.
Like give me some NMR data. That'll help me to determine. All right. Well, here's the answer. It's none. Why? Because if you draw in that H right there, and you draw in that H right there, those H's clash, steric clash, and it makes the ring do this. And once it does that, p orbitals may be overlapping theoretically. The clash makes it buckle. And it's actually a non-aromatic compound. Okay? What about the one over here? What's the difference? We remove the H's and just bond these together. Whenever you see something like this, these rings are said to be fused, but you still look around the periphery. Okay? And ignore that bond there. But, since we remove the H's, there's no clash, and naphthalene is an aromatic compound. 2 on the side. The only odd one is the one in the middle because of that clash. Okay? I think we got a couple. Is that?
It's like 8.
Oh, sorry. I can't see this shorthand on me. See some of you in lab this afternoon? Upstairs?